SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today I am going to talk about introduction to electrochemical microtexturing. I acknowledge the help taken from the following: the help by Professor Divyansh Patel, PhD thesis submitted to IIT Kanpur, then chapter on ECM in the book on advanced machining processes, and then advanced machining processes lecture under NPTEL program. On outline of the presentation are as follows: introduction to microtexturing, microtexturing processes, single multiple electrodes based microtexturing, texturing of hypodermic needles, development of atomized electrolyte flushing system, development of shape changing pulse power supply, and flexible electrode based through mass electrochemical microtexturing, and some inferences based on whatever has been reported from 1 to 7. Electrochemical microtexturing, nano microtexturing in nature. First let us understand where are micro nano texturing in the nature itself. Before that, let us understand what is surface texturing and texture in nature. Surface texturing is the process of creating a specific roughness appearance onto a surface in order to change its functional properties such as hydrophobicity, biocompatibility, antimicrobial, corrosion resistance, heat transfer, cleanliness, etc. Such properties achieved through generating a specific type of surface roughness on the object. Now let us see certain objects. Now this is nano micro textures in nature, as you will see here. This is a leaf and hydrophobic surface is there on this leaf, and this is dynamic lighting and viewing directions. Now there are certain textures where by changing the direction you will get different kind of colors. And you can see here the light diffraction on the this wing of the peacock. Now this has been taken from this particular reference. Now textures in nature, some other examples. You can see here, this is a insect, morpho butterfly wing is there. Now if you enlarge this very small area of this, you will find this kind of surface texture is there. So cell widths sizes correspond to visible light wavelength of 400 to 600 nanometer over here. If you further magnify if one particular small part of this wing, you will see this kind of the texture is there. The most common bits are about 400 nanometer. So it is much smaller than 1 micrometer itself. So you can see here nano microtexture in the nature, and this is has many properties as long as this particular part is concerned. Now let us see another hydrophobicity phenomena in the nature. This is another lotus leaf structure is there. You can see the lotus leaves are there, and we all know that if you put a drop of water, it will not adhere to the leaf, rather it will remain there and get out once you move it here and there. Now, if you magnify this leaf, you will find this kind of the structure where thousands of micro pillars are there. These are the micro pillars on this particular leaf, actual real life leaf. Now, if you further magnify this particular micro pillar, you will find certain hairs are there, and these hairs are nanometer in dimensions. Now, if you see them, they look like this. If you magnify this particular part further, they look like this, and these are in the nanometer sizes. We try to develop this schematic diagram for this particular part, and you can see this is the leaf, and these are the micropillars on the leaf, and over these micropillars nano hairs are there, and because of these nano hairs and micropillars, you have the surface as hydrophobic surface. We at IIT Kanpur have tried to develop this micropillar and also attempted to develop some nano hairs over it, although we could not get great success over there. As long as nano hairs development on micropillars are concerned. This is another example of colocasia and elephant ear that you can see over here. These are the micropillars on this particular leaf. This is the highly magnified view of this particular leaf, and you can clearly see these are the micropillars, and over these micropillars nano hairs are there. These are the nano hairs over here which I have shown over here. So, you can see micropillars, and there are some small pillars over these pillars, and these are the micropillars and nano hairs, and this makes it as hydrophobic surfaces. Now, this is the schematic diagram, and you can see that this is the contact angle, and this contact angle changes depending upon the characteristics of micropillars and nano hairs over there. Hydrophobic surfaces, some applications are there. Let us see certain interesting applications of hydrophobic surfaces in real life, and this is the lotus. You can have antimicrobial surgical tools, which is very important. Hydrophobic blood circulation pumps are there, and then you have ice phobic wings and engines of aircraft. This helps a lot as long as life of the engines is concerned. Now, you can see here hydrophobic fabric. This is the fabric, and these are the water drops. They do not get adhered on this fabric because they are the hydrophobic surfaces. They remain over there suspended or lying over there, and they can be removed from the hydrophobic surface or fabric very easily without wetting the fabric. Now, this is a very important application. Waterproof circuit boards are there. Now, you have this electronic circuits. If even a single water drop goes there and get adhered, then whole circuit gets damaged. But if the surfaces are hydrophobic in nature, then this water drop will not get adhered, and it will get removed or vaporized, and your circuit will not get damaged. So, hydrophobic surface on these electronic hydrophobic surface on these electronic circuits is very, circuit boards are very important. This is another interesting example. This gentleman has one as the hydrophobic surface shoe, another non-hydrophobic surface shoe, and when he goes into the mud, you can see this is quite neat and clean, which has the hydrophobic surface, and this is very dirty, which does not have the hydrophobic surface, and this is very important and very useful in real life. This is bioorganism proof ship hull is there. This is the hydrophobic surface. This is not the hydrophobic surface, and you can see the clear difference in the quality of the hydrophobic surface and non-hydrophobic surface. And definitely, if it is not hydrophobic surface, then the life of the ship will definitely get reduced substantially. So, this is how you can measure, see the water while repelling metal surface. You can see a metal surface or it may be other hydrophobic surface. So, this is being repelled from the surface over there. Microtexturing methods, there are various methods by which you can create the microtexture on the metallic and non-metallic surfaces. Microtexturing methods, let us see some of them. These are the traditional methods of microtexturing creation: micro turning, micro milling, micro drilling, etc. You can create the microtexture also. Then there are advanced micro machining methods, where or advanced micro machining methods, with the help of which you can create the microtextures or even in some cases nano textures also. So, mechanical type of methods are abrasive butter jet micro machining, ultrasonic micro machining. These are the micro machining methods, some of which we have already seen in the lecture on electrochemical micro machining. Now, these are the thermal methods like micro EDM, micro EBM, electron beam machining, micro laser beam machining, micro plasma arc machining. Then there are certain chemical like electrochemical micro machining, photochemical micro machining. Now, thermal microtexturing methods have certain problems, like you get heat affected zone HAZ. There are certain residual stresses which are there or which remain in the textured or microtextured surfaces. Resolidified edges and surfaces are there. Tool wear is substantially high, and feature resolution depends upon the machining conditions or texturing conditions that you select. You can see some of the methods over here. These are related to electrochemical microtexturing. Now, this is the tool. You are creating a channel over here. You are creating the dimples over here. This is the electrolyte. This is the electrolyte is coming in, and tool is there, and you can create these dimples over there. This is a single dimple creation in one go, but you can have the tool which has many minor tools, with the help of which more than one dimple can be created at a time. And again, this is used for creation of the channels. This is the electrolyte. This is the flat electrode over here. The spindle is there, and you are sinking it downwards. This is the workpiece, which is definitely electrically conducting workpiece material. So, you can see here, important thing to note, that this method, the tool is not touching the workpiece. It is just through the electrolyte and electrochemical reaction you are removing the material. So, it is contactless machining. Atomic scale material dissolution that we have already seen in electrochemical micromachining. There is no heat affected zone in electrochemical micromachining, and mechanical properties remain unchanged because there are no forces acting on the workpiece. There is no heat generation on the workpiece. Only thing is the material, workpiece material should be anti-corrosive, otherwise it will get damaged. Same thing shown over here for other applications, just like electrochemical microtexturing. You can see dimples are being created. This is the electrolyte, this is the tool, and this is the inter-electrode gap, and it is connected to, tool is connected to negative terminal, workpiece connected to positive terminal, and you can create the dimples over there. More than one dimple at a time can also be created. Now, this is the flat electrolyte jet, this is the tool, and you are able to create these micro channels. These channel width is in terms of microns. Again, this workpiece is rotating over the spindle, and you are able to create this circular channel, or you can also create these dimples on this, depending upon what type of motion for the tool you are giving and how this this is the workpiece, what kind of motion you are giving to the workpiece, or you can give the motion to the tool also. Electrochemical microtexturing, further you can see here there are two methods commonly used in real life for microtexturing. One is the maskless electrochemical machining or electrochemical microtexturing, you can use it, or through mask electrochemical machining or microtexturing. Now, you can see here direct write method. Now, this is for ECM. So, single tool can be used as we have seen in the earlier slide. You can use wire for creating that one, or you can use the jet also, all the three examples we have seen in the earlier slide. You can use multiple tools, which I told you that more than one dimples or more than one channels can be created in one go by using the multiple tools. Then you can have the sequential machining and this is the direct sinking method. Now, here you are not using any kind of the mask. So, definitely the dimensions or dimensional accuracy that you are going to get will not be as good as you get in case of through mask electrochemical microtexturing. Now, in this case I will show you the details in the following slides. Mask is being used and the area which is the bare area where there is no mask, the material is being removed from there. So, first thing is you have to prepare the mask. So, mask preparation or mask machining you can do with the help of laser machining, or you can also use laser machining then lithography. Direct sinking, jet electrochemical microtexturing can be done, electrode based microtexturing can be done. You can also use wire electrochemical microtexturing. Here you have to index the workpiece depending upon the type of the texturing you are creating. If it is a dimple creation, then really you need not to index the workpiece regularly. Some methods used for creating microtextures, you can see over here single micro tool based microtexturing. This is the single tool and you are creating the microtextures over here. This is the electrolyte and here is the workpiece where you are going to create the microtexture. These reactions we have already seen. Now, numerical and experimental analysis of single tool based electrochemical microtexturing is there. You can also use the simulation, or you can also do the simulation for what type of textures, what size of textures you are going to get, and you can compare the experimental and simulated results. Development of atomized electrolyte based electrochemical micromachining. Here atomized jet is being used for creating the microtextures. Phased here you can see this is the cathode and these are the multiple tools, and here is the workpiece and you are sinking it and you will find electrolyte is there and you will find that multiple textures are created over there. Multiple electrodes based microtexturing, textured tools fabrication through wire EDM, wire ECM and laser machining process for large area texturing. You have to develop the tool also that you can use either wire EDM process, wire ECM process or other processes also. Microtexturing on hypodermic needle, this is very important. This is the needle, hypodermic needle, and microtexturing has been done on this. We will see details, many details of this. Study of insertion force of various textured hypodermic needles. It was said that if we create the microtextures, nanotextures on this hypodermic needle, then when you are injecting it in the human body, then the pain relief takes place or the pain being felt by the patient will reduce. So, this study was done to some extent at IIT Kanpur and I will give you some results for this. Development of shape changing pulse power supply. It has also been reported that if you use different types of the pulses, just like a triangular pulse, rectangular pulse, sinusoidal pulse and so on, that also affects the performance of texturing process. So, some study has been done with reference to that also. Design and development of variable voltage waveform DC power supply. Now, you can see that there are the free form surfaces, curved surfaces where texturing or microtexturing, nanotexturing is very difficult. So, what Dr. Divyansh Patel has done it, he has proposed a flexible electrode which can adapt itself according to the shape of the workpiece, and that is known as flexible electrode, and then he has used it for electrochemical microtexturing. And here mask was used, that is why through mask electrochemical microtexturing. Development of a stamping device for texturing on flat. This device can be used for flat surfaces, cylindrical surfaces and free-form surfaces. So, this is a proposal which was made by him in one of the research papers, and it has proved to be very successful, especially in case of free-form and cylindrical surfaces. Methods of electrochemical microtexturing. Now, some of them I have told you in the earlier slides. This is the single dimple being created. Over here you can see insulation, this is very important, insulation is here, as I have told you in the lecture on electrochemical micromachining. Insulation plays very important role in controlling the dimensional accuracy and shape of the machined component, and this is the tool. Electrolyte is being supplied and you can create the micro dimples over here. Now, this is a cylindrical surface, you are rotating it, and this is the tool, and you are able to create micro dimples over here, and you have to control or manipulate the rotational speed of this particular cylindrical workpiece, so that you can create proper shape and size of the micro textures or the micro dimples over there. And you can see here arrangement of workpiece over there. Then we are, this is the epoxy resin, and this is the copper layer, and micro tool is there. You can see this is the micro tool, and here this is 75 micron size tool tip, and tool tip sometimes it was 90 micron size also. Sorry, I am sorry, this is 90.75 micrometer as the tool tip diameter over here. Now, you can see flushing, effect of flushing. These are the micro dimples that have been created, and you can see this is the effect. If sufficient or insufficient flushing is there, then somewhere this kind of surface is achieved. You can see here that from everywhere uniform machining has not taken place. At some places it is better, at some places it is very bad, like this, or like this, or like this. So, then there were some simulation results were reported by Dr. Divyansh Patel regarding the microtexturing using finite element method and other techniques, and this is the insulated tool he has used. This is the electrolyte, this is the 250 micron size tool is there, and you can see this is the insulation on the tool, and this is the kind of the dimples are created. So, he has simulated the results and he has performed the experiment, and he has compared both of them and found reasonably good agreement in them. Effect of process parameters on dimple diameter during single tool based electrochemical texturing and simulated results. Now, you can see here are the simulated results and experimental results. This is the machining time in seconds, and this is the diameter of dimples in micrometer, and this is the experimental results. These are the experimental results and these are the simulated results. So, you can see here the simulated results are not matching well in this particular case, because they are continuously increasing, while experimentally it is not like this, it is like this. Now, this is the basic explanation of this deviation is that there are certain assumptions made during the simulation technique or during development of the model for the simulation purposes, and that is why this much deviation is there, and those assumptions should be relaxed to get better agreement between the simulated results and the experimental results. Now, you can see here electrolyte conductivity is there, variation of electrolyte conductivity, and this is the diameter of the dimple, and you can see these are the experimental results or these are the simulated results, and slightly better matching is there compared to this in this particular case. And then you have the voltage, variation of voltage, and this is the diameter of the dimple, and you can see these are the experimental results and these are the simulated results. Actually, whether they are good or well matching or not well matching, one has to find out what is the percentage deviation between the experimental and simulated results. If the variation is more than 10%, that simply means you need to relax the assumptions or you need to modify the model of simulation, because 10%, beyond 10% deviation is not acceptable. Volume of material removed from anode, that is the workpiece, is proportional to machining time, conductivity and voltage, and the effect of all the three has been shown here, experimental as well as theoretical. Microchannels, microgrooves and micropillars. Now, let us see some results over here. These are the microchannels created. Here you can see they are 251 micron or 161 micron or 232 micron width of the microchannel is there. These are the microchannels created over here. The photograph is not very good, but you can clearly see these are the microchannels created. Now, this is the cylindrical workpiece and over which these microchannels have been created. This is one microchannel, another third one. Its dimension is 260 micron and it is 207 micron. This is not given. So, you can see that you can create these kind of the channels with the help of electrochemical microtexturing. In this particular case, you have to rotate the workpiece and keep the tool stationary. Now, these are the SEM photographs. You can clearly see the deviation even within the channel, how they are varying. Now, here you can see this is the part where these are the micro dimples that have been created over here. If you see the enlarged view of these dimples, these are the enlarged view of these dimples and their size is somewhere around 334 micrometer, or it may be varying 338 micrometer and so on. So, one thing you can clearly see, they are not exactly of the same dimensions, they are varying depending upon what are the conditions remaining at that particular point of time when these dimples are being created. So, this is an 317, but some part you have the nice dimple, at some places not so, because stray current effect can also be seen over here. This is the stray current effect over here also. So, this is the photograph, these are the micropillars that are being created over here. These are the micropillars you can see over here in the whitish color, and they have been created by this particular process. Enlarged view of this one you can see, and this is the one you can see. So, even the top surface of the micropillar is not very uniform. All this depends upon the type of the tool you are using, the surface finish of the tool and the flow characteristics of the electrolyte at that particular point of time. Electrochemical surface texturing, laser surface texturing. Now, you can see here microchannels array has been created in one particular direction, and this is the another micropillars array. Now, what you have to, you take this part and then create the channel perpendicular to this direction, and then you will get the micropillars something like this over here, because this is the one channel, one direction channel you have created here, and then in this particular direction another channel is being created to create the micropillars. You can see here these are the clearly visible micropillars in this particular case, and these are the channels over here. Now, contact angle on microtextured surface, this is the drop of water. This is another example of micropillars array. You can clearly see over here, these are the micropillars. This is the enlarged view of this particular part. Now, here these micropillars are very clearly visible. This is the again SEM photographs, micropillars array is there, and you can see. Now, what I mentioned earlier is that over these micropillars, if you can create the nano hairs, then really speaking it will give substantially large contact angle, and for the creation of nano hairs over here, you need to use an appropriate nano finishing nano surface finishing process. Effect of types of texturing on insertion force of hypodermic needle, which I have shown to you already, surface contact area and depth of penetration. Now, you can see here these are the surface contact area. In all the 4 cases this will be different. This is a cylindrical, these are the dimples, these are the channels, this is the cylindrical channel. So, all of them are in different cases. This is the case of the dimples over here, this is the linear channel shown over here, that is this one, and this is the circular channel, and this is the untextured surface over here. Now, so this tells you the surface contact area. Wherever surface contact area is smaller, forces will be smaller. Surface contact area is large, forces will be large. So, you can see here insertion force on needle with different types of texturing. Now, in this particular case untextured surface, you have the largest force. Then you come to this dimples, second this is the third lower force over here that you can see, and this is the case of dimples, and this is the untextured. And in this particular case, this is the linear channel is there, this is the linear channel, and this one is the circular channel. So, there is the minimal force in case of circular channel, and you can see here this is the circular channel and this is the minimum contact area in case of circular channel. So, wherever you have the minimal surface contact area, there the force will be minimal. What do we conclude from this? That if you have the minimal surface contact area on the insertion needle or hypodermic needle, then the insertion force will be minimal. That means the pain felt by the patient will be minimal. That was the objective of this particular work. So, insertion force is maximum with untextured needle and minimum with circular channel texture, because it has the minimal surface contact area that you can see over here. So, force is pressure into contact area. When you are inserting the needle, certain pressure is acting, and depending upon the contact area, patient will feel the pain. What inferences we can derive from this? Micropillars obtained, height ranging from 50 to 100 micron and width 250 to 300 micron, make it possible to produce hydrophobic surfaces. Developed numerical model of EC microtexturing process, not discussed here in detail. For producing micro dimples, he has used COMSOL 4.3 software on stainless steel surfaces that predicts the profile with minimal error. However, as I have told you, if the deviation is more than 10%, then really speaking it is not acceptable and you have to improve upon the model. So, problem shown through photographs, as you can see here, non-uniformity is there, high overcut, undissolved bumps are observed there, we have seen in some of the photographs shown earlier, and geometrical errors are there. So, needle microtexturing, in some case of the textured needle micro grooves, the insertion force obtained is minimum 0.56 Newton as compared to other microtextured needles. Surface area not in contact is found to be maximum in case of micro grooves. So, lubrication is effective in the case of micro dimples. since it can hold oil droplets during insertion. So, this dimples also help in retaining the lubrication or lubricating oil. So, that helps in reducing the frictional forces. Reason: insufficient flushing and offset pulsed voltage. Now, why these problems were there? Because of this. Electrochemical microtexturing using atomized electrolyte. So far what I have shown to you is that while microtexturing we are using the tools, it may be a single tool, it may be a multiple tools, and there were certain problems which I have discussed. Now, we used also the atomized electrolyte. Let us see what it is. This is the atomized electrolyte. Now, you have here you have the electrode is there, and this is electrically conducting. So, this electrolyte itself is acting as a tool. So, you can have different ways of this electrolyte jet, flat fan like this, full cone like this. This is the fan, you can see here. This is the full cone over there, something like what shown over here, and full cone over here also slightly different. This is the hollow cone. So, you can see here electrolyte is only on the outer periphery, in between the hollow part is there, and there is no electrolyte over here. So, it will machine only from this area, and this area will remain unmachined. This is very important and useful. And then you have straight single point distribution like this. So, this is the another way. Concept of atomized electrolyte flushing, how does it work? Let us see it. Transverse motion is there, this is the electrolyte droplets are there, and this is the tool, here is the workpiece, and this is moving, and whenever it is in contact it is working over there. Then you have the rebound, some of the droplets may rebound over here and go out. They are just moving like this, but here it is rebounding and moving away from the workpiece surface. Somewhere in some cases you have the spread like this, and this is remaining over there for a very short period when you are supplying this electrolyte over here, and this is the tool, and somewhere a splash is taking place like this. So, these are the regimes of atomized electrolyte flushing. This is the droplet hypothesis. Now, you can see here hydrogen bubbles are there, electrolyte drop is there, ferrous hydroxides are created over here, and this is the iron, and this is the dimple being created over there. This is the kind of the concept that or hypothesis that was developed. Now, atomized electrolyte dissolution, this is the workpiece, and this is coming over there, going through this, and the gap, this thickness of this is the atomized electrolyte dissolution. Thickness is 30 to 100 micrometer. This is very important to note, because we want this as small as possible, and current density distribution is like this. That means it is maximum at the center and dropping like this. But conventional electrolyte dissolution, where in conventional method where we are not using the jet, then the electrolyte distribution is like this, very thick layer is there, and this creates lot of other problems during machining. So, this is the electrolyte jet, and velocity is 1 to 5 meter per second, and this gap is somewhere 500 to 2000 micrometer, and this is the current density distribution. So, there are certain advantages of using atomized electrolyte flushing, especially in case of micromachining or microtexturing. Now, what you get? Reduced electrolyte consumption in case of atomized electrolyte texturing. 56 milliliter per minute leads the process towards sustainable manufacturing. You can see here various pictures. Thick film with conventional jet is being created over here. Now, then thin film with atomized electrolyte is, this is the atomized electrolyte, and you can see very thin film is created, we have seen in the earlier one, and this is the one you can see over here. This is the tool, and this is the atomized electrolyte over here, and this is able to machine the or drill the holes over it. You can see here diameter and voltage. You can see the this is the depth. So, as the voltage is increasing, diameter is increasing. As the voltage is increasing, depth is also increasing. Now, because with the higher voltage you are supplying the higher energy, higher dissolution is taking place, faster dissolution is taking place. So, you get the deeper hole and larger hole with the increase of the voltage, because higher voltage will give you the higher current density, and higher current density means higher material removal rate. So, electrolyte pressure and impingement angle play important role in electrolyte film thickness and velocity. Hence, reduction in stray current at 45 degree of impingement angle, the maximum depth and best profile is obtained. So, this impingement angle is also important, and one has to be careful while setting the jet, electrolyte or atomized electrolyte jet angle with reference to the workpiece, because at 45 degree you get the best results. Influence of electrolyte mixed pressure on geometry of micro dimples. You can see over here, this is at 1 bar, and this is the kind of the geometry you are getting of the dimple, and here you can see this is the profile 1 and profile 2 are seen over here. This is the diameter, this is the depth. So, this is the diameter is increasing. Here diameter is almost constant, depth is increasing with pressure. This is the 3 bar diameter, 3 bar pressure you can see, and you can compare this with this one. 1 bar, it is not that neat and clean as this is there, 3 bar is there, and this is the profile, and you can see 1 and 2 things are there. This is at 5 bar, again problems are being created at 5 bar, because you can see this is not good, this is also not good, here also it is not good. So, that means there will be some optimum pressure at which you will get the best profile of the dimples, means width as well as depth. So, you have to optimize the parameters before really using it on the shop floor for creating the dimples on the products. There is significant increase in depth of micro dimples is observed due to the improved flushing. From 1 bar to 5 bar, 50% of depth increment is observed. You can see another example. This is profile 1, profile 2. Enlarged view of the previous one. Comparison of conventional atomized electrolyte ECMM. This is the conventional electrochemical micromachining, and you can see here, this is the picture of the dimples created, this is the SEM picture, this is the enlarged picture, you can see over here. Then this is with the atomized ECMM, and qualitatively if you compare these two, there is a difference in the cleanliness of the dimples that have been created over here. If you compare this one with this one, again you find this atomized one as the better results compared to the conventional electrolyte flushing. So, you can see over here compared to this, some differences are there. So, what we can conclude from here is that atomized electrolyte supply in electrochemical micromachining gives better results. You get better geometrical accuracy improved with the atomized electrolyte. Further studies required: suitability for multiple electrode based ECMM and optimization of the spray type of enhanced flushing, frequency and different shapes of pulse power supply for electrochemical microtexturing, because as I mentioned in other lectures also, that you can have the pulse power supply with different shapes, as we will see here. Frequency and different shapes of pulse power supply for electrochemical microtexturing. Let us see their effects. Now, here you can see shape changing with high frequency pulse power supply for electrochemical microtexturing. These are the square shapes of the pulse powers. This is the sinusoidal one and this is the triangular one. We have conducted experiments with all the three as shown in the following slides. The question is, why do you need different shapes of pulses of power supply in pulsed electrochemical micromachining? Development of a new low energy distribution high frequency pulse power supply with addition of shape changing capability to check whether it enhances the texture's quality, because the quality of the texture is very important, because the performance of the texture surface will depend upon the quality of the texture. Why? Different shaped pulses should change the current distribution over the machining area, and if current distribution is changing, then definitely the textured surface characteristics is also changing. And different pulse shape for DC power supply are considered, like rectangle, triangular and sinusoidal shapes. I will show you. Now, effect of pulse frequency and pulse on time on quality of the features. As you can see here, this is the pulse frequency, this is the overcut, because overcut controls the quality of the textures that you are creating. Now, this is the drilling, this is the sinking, this is the sinking one and this is the scanning one. So, you can see here pulse frequency is making lot of difference as long as overcut is concerned. If it is low pulse frequency, very high overcut is obtained, and we are not interested in having the high overcut. And if you go further, it is in megahertz. If it is beyond 5 megahertz, then this overcut is substantially reducing, and at 9 it is further reduced. So, we should have the high pulse frequency to get better quality of the textures. Now, you can see here, this is the 900 nanosecond, this is 700 nanosecond, this is 500 nanosecond and this is 300. So, you can see with this change you are getting the different characteristics of these dimples that you have created over here. Simulated current density profiles for different pulses. Now, for 3 pulses, as I have told you earlier, rectangular, sinusoidal and triangular pulses, we have tried to simulate the results, and you can see over here, this is the triangular one, this is the sinusoidal, this is the rectangular one, and these are the shown over here in schematic. These are the actual photographs. Now, we will see here, this is the profile that we have obtained. If you see, this is for square one, this is the square one, that means depth obtained in case of square pulse is maximum. This is the sinusoidal one. So, this is for sinusoidal one and this is the triangular one. Now, all the 3 are giving different depth of the dimples or whatever feature you are creating, and different overcuts also. So, comparative plot of anode profile simulated after 30 seconds. These are the simulated results, please note it carefully, of machining for rectangular, sinusoidal and triangular voltage pulses. So, you can see that. So, there was the experimental setup which was used for creating these features with these 3 different types of the pulses. So many components are sold. This is the function generator, power supply. This is the oscilloscope where you can see what shape and size of the pulse power is being used. You can see one of them, square one shown over here. The current amplifier and other details are there. Now, here this is the electrolyte feeding, electrolyte jet is there, macro tool is there, workpiece is here on which you are creating these textures, and then this is the electrolyte tank, you are supplying the electrolyte from here, and this is the tub in which this electrolyte is collected and electrolyte bubbles are creating over there. These are the different parameters. Influence of pulse frequency and shape on diameter of the micro dimples that have been created. See it very carefully. Now, here this is the diameter in micrometer, and here you can see triangular shape, sinusoidal shape and square shape. So, maximum diameter is being given by the square shape and minimum by the triangular shape, but if you see the quality, then that makes a difference over here. These are the three different ones and these are the another one. This is the frequency. So, you can see the overcut over here. This is the rectangular one, maximum overcut, sinusoidal lesser one and minimum is in the triangular one. So, what I can say is that the triangular one is giving the better quality compared to other two pulse shapes, and this is the one which you can see over here, and as you are increasing the frequency, the overcut is further decreasing, and this was conducted up to this particular frequency. So, comparison of rectangular, sinusoidal and triangular pulse voltage machining, micro dimple depth versus frequency. This is the frequency, this is the overcut, not the depth. So, you can see here, this is for triangular, this is for the triangular one, this is for the sinusoidal and this is for the square one, and maximum largest one is there, but these are the areas where from we do not want to remove it, the material. So, accuracy is not very good in this particular case compared to this case. Same is the case over here, this is the better quality, this particular one, that is the square one. Experimental validation of developed model. Now, you can see here experiments were conducted with the setup, and these are the three different channels that have been created. This is with rectangular pulse shape, this is with sinusoidal pulse shape and this is with triangular pulse shape, and you can see the variation in the width of the channel, or you may say overcut over there is larger in case of rectangular one compared to triangular one. You can see the for different ones, anode profile for rectangular voltage pulse, this is the experimental one, this is the simulated one. There is a reasonable deviation between the two in this particular case, as you can see, and this is for sinusoidal voltage pulse, this is the experimental one and this is the simulated one. Not very good, variation is there, continuous variation is there here also, here also. So, the control of the parameters was not very good, but it gives you the comparison of the two, and this is slightly better compared to these two, not very good because lot of variations are there also, but slightly better matching with the simulated results, as compared to other two cases. This is with the triangular pulse voltage. So, you can see here that triangular pulse voltage, triangular pulse shape of the voltage gives slightly better results compared to other two for which experiments have been conducted. This I have already shown to you. Now, there were same conditions in different cases. Now, again let us see micropillar array machined through atomized electrolyte electrochemical microtexturing. These are the micropillars which have been created, and you can see here textures, waviness and roughness. So, this gives you the roughness, and these are the textures and waviness over there, slight waviness is also there. You can see the micropillars created over here, the same one, and you can clearly see they have been created by creating one channel in this direction, another channel in this direction, you get these micropillars. This is the another case, diamond micropillars, diamond shaped. This is the diamond shaped micropillars that have been created over here, because it is very difficult to create the micropillars of different shapes. And this is the curved micropillar array on stainless steel 304. These are the curved micropillars created on the curved surfaces. So, what I am trying to show here is that you can create the micropillars either flat or curved or diamond shape and so on. So, you have to design the mask accordingly, according to the shape of the workpiece on which you are creating the micropillars. If you are doing it through mask electrochemical microtexturing, and then only you are going to get better accuracy compared to without mask electrochemical microtexturing. Now, you can see the effect. This is the surface where repelled this drop of water is being repelled, and this is the hydrophobic surface, and the angle you are getting approximately 98.8 degree. Some inferences are there. The intermittent supply of voltage provides ideal time to flush the hydrogen bubbles and sludge from the machining zone, and also increases control over the dissolution process, because whenever you are having the pulse power supply, you are providing the time for the removal of hydrogen bubbles and sludge from the interelectrode gap. If it is a continuous DC, then this characteristic will not be there. On increasing the pulse frequency, the average diameter of the dimple reduces, that we have seen earlier also. The percentage decrements in the diameter of the dimple is maximum when changing from rectangle to triangle waveform, and in between from rectangle to sinusoidal. In pulse electrochemical micromachining, minimum overcut can be achieved even at lower pulse frequencies by reducing the pulse energy by changing the pulse shape. The finite element model developed in MATLAB predicts the anode profile with an average deviation with experimental results of 18% in all the three types of the voltage pulses. I have already mentioned that if it is more than 10% or so, then it needs further improvement in the model. So, it is reasonably high as long as 18% is concerned. Flexible electrode through mask electrochemical machining or micromachining, large area microtexturing on free form surfaces using flexible electrode through mask electrochemical machining. This is important, please note, see it, this is the sponge and this is the mask and this is the workpiece, and this is the silver cloth. This is the silver cloth which is flexible, which can change its shape. Now, you can see here sponge, this is the silver cloth, this is the mask and this is the workpiece in the curved shape with curved surfaces. Flexible electrode based microtexturing, the USA around 6 lakhs total knee replacements per year are there. This is very important application, biomedical application of textured surfaces. For improving performance of knee joint and hip joint implants, reduce their wear and increase the life by implying microtextures on the sliding surfaces, because both of them have the friction, both of them have the moving action, and as a result of that, if you can have the textured surface and reduce the coefficient of friction, then definitely the life of the implants will increase and the pain to the patients will decrease. Microtexturing on artificial biomedical implants enhance sustainability and life cycle. The question is how? By better implant tissue interface, cell addition and cell polarification. Microtextures reduce the friction coefficient, entrapped wear particles may be released from the dimples. You can see here, very important, these are the micro dimples that have been created on the implants, and this is a knee joint. This is the hip joint, these are the dimples that have been created over here, and because of this texture surface the friction will be reduced. Now you can see here again how it is being done, that can be seen over here. We are using this jet flushing, atomized jet flushing over there, and you can see here this is the mask is there, electrolyte is being supplied over here, this is the tool is there, this is the workpiece, and you can see these are the final shapes. Before machining is like this, after machining it is like this. Now let us see porous flexible electrode based through mask microtexturing. A porous metal cathode is used to remove the electrolyte products and generate deep micro dimples by using an open reaction unit instead of an enclosed one. Now you can see here, this is the electrolyte over there, this is the mask over there, the tool is there, and this is the workpiece, that is the anode, and you can see here reaction products and gas bubbles are being formed, and you can see they are taken. This is, since it is porous, so reaction products and gas bubbles, they are coming out from here, and that is the advantage of porous one. And you can see here, this is the before machining and this is after machining. So these are the different arrangements that have been shown over here. For Chen et al. Has proposed electrochemical micromachining of micro dimple arrays. Now here you are able to create the micro dimples. Mask is there, these are the holes in the mask, and this is the workpiece, and electrolyte is coming which is there, and tool is connected to the negative terminal, workpiece is connected to the positive terminal. So what is instead of continuous electrolyte flow like this, Divyansh Patel has proposed the jet electrolyte supply. This is the porous sponge one, and it is mask is there, workpiece is here, and this is the electrolyte which is removing the material from the workpiece, as you can see over here, and these are the gas bubbles and reaction products are there from the workpiece. And since it is sponge one, so the reaction products, very fine reaction products and gas bubbles, they will get exiting through this also. Now you can see here flexible electrode based microtexturing, as we have seen in the earlier slides. This is the one where you have the micropillars created. This is the photographic view, and here you can see the profiles and textures over there. Again same way, this is the SEM photograph, this is the picture of the same one. Now this is the another one, you can see clearly these are the micro dimples created of micro dimples of approximately 20 micrometer over here on the stainless steel sheets. Flexible electrode based microtexturing, this is the square one. Now zigzag pattern is there, as you can see over here, these are the square ones. This is the masked hemispherical surface over there, and this is the flexible electrochemical texturing through shape adaptable porous electrode is there, and it can adapt according to the shape of the workpiece. Microtextures array machining on a knee joint. Now this is the knee joint, and on this you can see here the microtextures are being created, and I have already mentioned, if microtextures are there, friction can be reduced and pain to the patient can be reduced, and life of the knee joint can improve. These are the different kind of the textures can be created, and you should know that these knee joints have the free form surface. So it is very difficult to create by other methods the correct type of the microtexture. So this flexible flexible porous electrode can be used for this particular purpose. Now, these are the kind of the textures that have been created, and these are the SEM photographs of the same square micro dimples of 100 micrometer bits that have been created over there. Some inferences we can make: micro textures like dimples, channels, pillars, etc., ranging from 20 micrometer to 150 micrometer have been successfully made. The device is capable of texturing approximately 10,000 micro features of approximately 100 micrometer dimension in 5 minutes, which is quite large. So, the flexibility of the electrode as well as mask is tested by experimenting on cylindrical, spherical and a free-form surface of a knee joint. A highly durable, low thickness mask is needed to be researched for less than 10 micrometer. Now, this is what we have already done: single electrode electrochemical micromachining, multiple electrode electrochemical micromachining through mask ECMM, texturing on flat and curved surfaces, multiple electrode array fabrication, numerical simulation and parametric analysis, micro dimples, micro channels and micro pillars, hierarchical microtexture. All this what we have already discussed, I am trying to show it here to you. And adequate electrolyte flushing, ultra short voltage pulsed for better localization of dissolution, and then high resolution mask fabrication, 3D numerical simulation for pitch determination, and micro pillars, micro channels, micro dimples, all of them have been created, and I have already shown to you. Textures on cylindrical surfaces have been done using this particular process, and texturing on free form surfaces also has been done, especially for the knee joint and hip joints. So, what we have done in this particular lecture is what is microtexturing and their applications, different types of processes used for microtexturing, single multiple electrode based microtexturing, texturing of hypodermic needles, development of atomized electrolyte flushing system, and development of shape changing pulse power supply. And finally, we also discussed about the flexible electrode based through mask electrochemical microtexturing and their applications. Thank you very much.